Hello again, everyone. So this is my third talk on the topic of singularities of Lagrangian mean curvature flow. Today, I'm going to be talking about translators that can appear as blow-ups. So again, this is all joint work with Jason Lotte and Felix Schulze. Okay, so the setup is essentially the same as before. We have a Lagrangian mean curvature flow inside C2. We have the same assumptions, bounded Lagrangian angle, bounded area ratios, and exactness or rationality. If you remember, the result that I stated is the following. So let's suppose that we have some singularity at the space-time point xt along our flow, and the singularity has a tangent flow, which is a union of two planes. Okay? Any union of two planes. Then the consequence of what we show is that any blow-up at this point is going to be either static or a translator. Okay, but this is really a consequence. You'll see in a second that the main result is really about translators, and that this is just a way of phrasing the result in terms of blow-ups. Okay, so let's recall what these blow-ups are. Well, the blow-up, remember, just meant that we choose a sequence of points in space-time converging to the singular point. We also choose a sequence of scalings that go to infinity, and then the blow-up is a weak limit of the sequence of rescaled flows that we obtain from that. And then in general, this blow-up will be an ancient flow, so it will exist for all negative t, or depending on what scales you chose, it will also often be an eternal flow. But okay, at the very least, it will always be an ancient flow. So now the whole point of the assumption that I made about the tangent flow was to get an entropy bound for this blow up L tilde t. Okay, so it's quite easy to show using the monotonicity formula that this blow up LT satisfies a so-called entropy bound. So this is the entropy defined by Kolding and Minikotzi. So it says that basically at all scales, we have this Gaussian area bound of 2. The 2 is because of the two planes. So now, if you have an ancient flow, then we can consider a blowdown at minus infinity. So this is kind of like a tangent flow, but instead of analyzing a singularity, we analyze the large scale behavior of L tilde t. Okay, so we now consider a sequence of scales going to 0, and we're looking at these, again, the same sort of parabolic rescalings of the flow. It defines a sequence, L tilde kt, and again, we can pass to a subsequential limit, L tilde infinity t, as k goes to infinity, and the same sort of fundamental result of Neves about tangent flows applies in this case too, and that says that L infinity t is a union of planes, using that we're in C2. And the entropy band that we wrote down says that this limit is at union of at most 2 planes. So now, okay, so remember this blowdown is basically saying what happens sort of far in the past on our blow up flow L tilde. So Lambert, Lotte, and Schulze have this very nice result that if you have an ancient flow, L tilde t, and if you have a blowdown, which is special Lagrangian, then actually the whole flow is special Lagrangian. So this is a fairly quick consequence of the fact that the Lagrangian angle satisfies the heat equation. So morally, if it's already sort of constant at time minus infinity, then it's actually constant at all times. At the same time, there's this result of Neves, which I I already mentioned, but this is the version for blowdowns instead of tangent flows. So it says that if this blowdown L tilde t infinity is a transverse union of two planes, which is not special Lagrangian, then actually the whole flow is just a union of two planes. So in particular, the whole flow is just static. So this is analogous to saying that if a tangent flow is a non-special Lagrangian union of two planes, then actually no singularity is forming. So it's more or less the same argument. So if you combine these 2 points, then there is only one case left. And this is the situation where the blowdown of our ancient solution is a union of 2 planes where, so it has to be a non-special Lagrangian union. Otherwise, we already know that the flow is static. And it cannot be transverse, because then we would know from Nevis's result that it's static. So it has to be a union of 2 planes with different Lagrangian angles where the intersection is a line. So we're studying ancient solutions of the flow that admit a blowdown that is a union of planes meeting along a line. So the main result is the following in this talk, this theorem due to Lotte, Schulze, and myself, that says that if you have such a tangent flow at minus infinity, sorry, a blowdown at minus infinity, given by 2 planes meeting along a line, then actually the ancient solution is a translator. Okay, so let me introduce some notation. So, okay, we're working in C2, and I'm going to choose 4 real coordinates, okay, in such a way that if I have my 2 planes which meet along a line, then the line is given by the z-axis, and the planes both are in this 3-dimensional subspace given by w equals to 0. Okay, so the planes meet along a line, so they span a 3-dimensional subspace. Okay, w is the coordinate that vanishes on both planes. Okay, so now the basic idea is the following. So okay, remember we have this ancient flow L tilde t. We want to use that we have a bunch of functions that solve the heat equation along this flow. Okay, so there's the constant 1, there's the Lagrangian angle, and there are the coordinate functions x, y, z, w. These are all solutions of the heat equation along the mean curvature flow. What we want to do is analyze what these functions look like as t goes to minus infinity. And the end goal is to use their asymptotic behavior to, in the end, show that w is actually in the span of 1 and theta. So the very heuristic idea here is to exploit that by assumption, w vanishes on the blowdown at minus infinity. So that suggests that somehow w should have sort of less than linear growth. Okay, the x, y, z sort of grow linearly. The w should somehow smaller than linear. And then we want to show that basically these 1 and theta exhaust all the possible functions, all the solutions of the heat equation with the sublinear growth. So then w has to be in their span. And then a very simple calculation shows that in that case, our flow is actually a translator. Okay. So once again, just like when studying tangent flows, it's actually much more convenient. At least I have been converted to this point of view of studying the rescaled flow. Okay, so in this case, we do this rescaling basically at the space-time origin. And what we're interested in is what happens when s goes to minus infinity. Okay, so when s goes to plus infinity, then this rescaled flow would converge to a tangent flow at the space-time point 0, 0. Okay, but now we want what happens at minus infinity. So as you go to minus infinity, then different subsequential limits of this flow will extract different possible blowdowns of your ancient flow L tilde. Okay, so we had these coordinate functions which satisfy the heat equation on the original flow. So it turns out that these kind of rescaled versions of these functions will satisfy the drift heat equation. So we've already used this in the case of theta. Okay, notice that this rescaling, this is really just x on the original flow, okay, because of this factor e to the s/2. So if you take this quantity on the rescaled flow, this is just the same as x on the original flow. Okay, so let's call these sort of normalized coordinate functions x tilde, y tilde, etc. Okay, so then we need to somehow make a little bit precise what we mean by the asymptotics. So what you do is if you have any solution of the drift heat equation, so any solution of this star on this rescaled mean curvature flow ms, then as you let s go to minus infinity, you can take a sequence, and at each time slice, you could renormalize the solution u to have, say, L2 norm 1, and then you can try to pass the limit of those. And in general, you would like to show that this limit will be a solution of the same equation, but on the blowdown. So here there is a major technical difficulty, which is that our blowdown is two planes meeting along a line, and that this line has real codimension 1 inside this union of two planes. So it's not difficult to show that if you do this rescaling procedure, then we will obtain two solutions of this drift heat equation on the two planes away from the intersection line. Okay, but the key difficulty is that a codimension 1 subset is typically not removable for solutions of the heat equation. So in fact, the Lagrangian condition plays a key role here to show that even though the blowdown is two planes meeting along a line, in a certain sense, the flow itself is not really connected along the whole line. So that there are only sort of relatively few points where the flow roughly looks like two different sheets which only interact at relatively few points. Okay, so in fact, this two limits that you get of the two solutions of the drift heat equation that you get on the two different planes on your blowdown, they can be extended in a suitable sense across the singular line. Okay, so the effect will be that from any solution of the drift heat equation on ms, what we obtain is two solutions of the drift heat equation on the two planes. They don't have to agree on the line, it's just two kind of independent solutions of the drift heat equation on the two planes. Okay, so effectively the flow is such that somehow it's more or less two different components that don't really interact or interact very little. Okay, so now, since we have a solution on these two planes, we can look at, well, what are the, we can classify these solutions. Okay, so on a single plane, the solutions will be simply given by a constant, which will be a degree 0 solution, and then these kind of rescaled coordinate functions, say x and y, if x and y are the two coordinates, and then higher order or higher degree solutions, so solutions that grow faster than e to the minus s/2 as s goes to minus infinity. So now if you have two planes, then you have two such functions. So there will be a two-dimensional space of constant functions, And then notice that since the angle theta is going to differ on the two planes, we can actually say that these two independent constants can be written as something in the span of the function 1 and theta. Okay, so you could imagine that theta is like plus or minus 1 on the two planes. Okay, so this gives us a two-dimensional space of degree 0 solutions. Then, if say x and y, sorry, say x and z were the coordinates on P1, then we'll have these two solutions. If y and z were the coordinates on P2, then we'll have these two solutions, the second and third. But altogether, these only give us a three-dimensional space, whereas we should have a four-dimensional space. If you have solutions on the two planes independently, you have a two-dimensional space on each plane. Okay, so again, if you think about it a little bit, you can write one more function in this form, theta e to the minus s over 2z, where again, theta is two different constants on the two planes. Okay, so in some sense, you could think of this as just plus or minus e to the minus s over 2z. Okay, so it's worth just thinking about the fact that this way we get that the span of these four functions will give you all possible combinations of the two solutions on the two planes. Okay, and notice that we couldn't have put w because w just vanishes. So that's not actually a solution. Right, that's just 0. Okay, so remember, the goal was to show that this sort of rescaled coordinate function w tilde on our rescaled flow is actually in the span of 1 and theta. So the kind of asymptotic version of this, as s goes to minus infinity, would say that, well, if we take this w tilde on ms and we do this rescaling procedure that I mentioned to extract a solution of the drift heat equation on the union of planes, then we want to show that this limiting solution is in the span of 1 and theta. Okay, so it turns out that once you know this, then basically it means that the growth of w tilde on the original flow was such that it can only be something in the span of these degree 0 solutions. Okay, so really we want to analyze the kind of asymptotics of our w tilde. Okay, so I'm glossing over a lot of like technicalities here, but heuristically, what's happening is that, well, w tilde by assumption vanishes on the blowdown. So that will tell us that w tilde has a slower growth than x tilde, y tilde, and z tilde. So somehow morally, you would expect that the w tilde infinity should not involve these functions. Okay, this is kind of, I'm lying a little bit, but this is just the heuristic picture. So you should not really worry about these so much. And then the only thing left is this theta z function. Okay, so here is the kind of key geometric idea that you have to notice. Okay, so the main difficulty is to show that this asymptotic limit cannot be this last remaining sort of degree 1 function. Okay, so we have the following geometric picture if you think about what this means. So we have this rescaled flow ms, where we're taking like a sequence of s's going to minus infinity. We're looking at this rescaled coordinate function w tilde, and we're trying to rule out that it looks very close to this function. Okay, and then just remember that you have to sort of normalize it. So in practice, it's going to look like some sort of epsilon times this function. Okay, where epsilon is like the L2 norm of the omega tilde at that time scale. Okay, so once again, there are really a lot of technicalities to deal with, because we do have a flow that's very close to something singular. So in this case, this union of two planes meeting along a line, we have a very large singular set. But it turns out, so again, this goes back to ideas of Neves, that at suitable times, one can show that actually the flow MS decomposes into two pieces. There will be two components, sigma 1 and sigma 2, at least in some fixed ball, B1. And the two components are very close to the two planes, P1, P2, in the blowdown. Okay, so it's not that there's no connection between these two pieces of MS, at least at this one certain time. But now our assumption was that this W coordinate looks roughly like, epsilon times theta z. And you can imagine theta as being just like plus or minus 1 on the two planes. So what that is saying is that on these two components, the W coordinate, so these two components are very close to these two planes. W vanishes on the two planes, but on the two components, it looks a little bit like plus or minus epsilon z. Okay, so roughly speaking, we have this picture. But then let's think about what this means. So here is an attempt at drawing this. Okay, so here what I'm drawing is maybe this, you can imagine this happening in the unit ball. And what I'm doing is this direction is the z-axis. So over on this side, you can imagine that this is some sort of slice where z equals -1. This is a slice where z equals +1. And what I'm trying to, so the plane of this screen, this is the XY plane, and W goes in and out of the screen. So what I'm indicating here is that when z is -1, then negative z, negative W would mean coming out of the plane. So when z is -1, then on sigma 1, W is a little bit negative. So this is what sigma 1 looks like inside the cross section. Z equals -1. So the way I'm trying to draw it is that it's a little bit above, like coming out of the screen. Whereas on the sigma 2 component, W is positive when Z is -1. So this piece is a little bit going into the screen. Okay, so the sigma 1 sort of lies above sigma 2 over here. Okay, so sigma 1 and sigma 2 are surfaces, and I'm taking this cross section in these slices where Z is constant. So these cross sections should be curves. Okay, and the Z equals -1 slice, the sigma 2 curve sigma 2 lies below the sigma 1. And then, okay, at Z equals +1, the sign switches. So there, it's sigma 2 that lies above sigma 1. And now, if you think about it, to go from this side over to this side, it must be the case that at some value of Z, these two curves have to intersect. Okay, in other words, that surfaces sigma 1 and sigma 2 have to intersect at some point. Okay, so as Z ranges from -1 to 1, we will find some intersection point, because these relative positions of sigma 1 and sigma 2 switch as Z increases. Okay, but if sigma 1 intersects sigma 2, what that means that at that time, at that very special value of S, this MS actually has an immersed point. But if you have an immersed point, then that means that the monotonicity formula it might be easier to have written down something, but it's a very easy consequence of the monotonicity formula that in that case, actually the flow MS is just static, because the sort of Gaussian area at very large scales is at most 2 by our entropy bound, whereas the double point, so this immersed point, means that there is some very small scale at which it's actually equal to 2. And the monotonicity formula says that this Gaussian area decreases at smaller and smaller scales. So in fact, it has to be equal to 2 at all scales. But that means that actually the flow is just a shrinker and in addition a cone. So it will be a static flow. So it will just be a union of 2 planes. But then this contradicts, I mean, this says that actually W is constant. And then this contradicts that it could have been this theta. So it cannot be this theta. It cannot have this asymptotics e to the minus s over 2z. Okay, so this rules out the bad case, and eventually, using a few more arguments, this shows that, okay, in fact, W is in the span of 1 and theta as required. And as I said, this is enough to show that the flow is a translator, and that was our main result. Okay, so this is the end of my sketch of the proof of this result. So, just to finish this series of lectures, let me mention just a couple of questions that naturally arise. Okay, so in these talks, I discussed 2 very special tangent flows. One was the union of 2 transverse planes. The other one was a union of 2 planes meeting along a line. So you can all imagine lots of other possibilities. I mean, maybe the simplest thing to try is what happens in higher dimensions. You could also talk about tangent flows given by planes there. So it turns out that the result I discussed in this talk, so about translators, does extend to higher dimensions. So even in higher dimensions, if you have a tangent flow given by 2 planes meeting along a line, then again, the flow is a translator or a union of 2 planes. At the same time, the other result, so the neck pinch statement, that's still open in higher dimensions. So now you can also ask for more planes, 3 or more. You can also ask about planes with multiplicity. Perhaps the most obvious question here is, what if you had a double plane? And maybe in a different direction, what one would really like to understand is, do you actually have to worry about these? Maybe the better thing, instead of analyzing every possible case one by one, the better thing might be to just show that actually for a generic flow, so for a generic initial Lagrangian, these other weird ones never happen. Perhaps it's the cases that, say, in 2 dimensions, the only generic tangent flows are the 2 that I've discussed in these talks. Okay, well, we would, going back to the tangent flows we looked at, we would also like to have more information about this case, the second situation where we have 2 planes meeting along a line. So conjecturally, if this happens, then Joyce's program says that actually we did something wrong, because if this happens, then the flow, it should not be possible to continue the flow in a graded Lagrangian way. So what Joyce says is that actually you should have done something much earlier to avoid the situation. And one of the first steps towards understanding that would be to show that if this does happen, then actually there's a holomorphic disk with boundary on the Lagrangian whose area is going to 0 as you approach the singular time. So this is a very interesting question, to how to prove the existence of such a holomorphic disk. Then the second thing that we would like to understand is a little bit more about the actual singularity formation. So I mean, this is certainly, these 2 are very closely related. So more specifically, what we would like to know is, if you have such a tangent flow, then can you always extract a type 2 blow up, so a smooth, non-flat blow up, which is given by this specific translator constructed by by Joyce, Lee, and Sui. So this would be analogous to the result in my previous talk that says that in the two transverse planes case, there's always a blow up given by a Lawler neck. So here you'd like to say that there's always a blow up given by this specific JLT translator. Okay, so I think that's enough for now. So thanks again for listening.